In this video, I'm going to be going through one of the breadth in chemistry papers that was from 2021. So this video will be in two parts. So the first part of this video, I will go through the multiple choice section. And in the second part of the video, I'll go through the second section with the longer answer questions. So breadth in chemistry then is one half of the AS component. In terms of question style, they tend to be quite short, short, snappy 1, 2, 3 markers. However, it does cover the entirety of AS chemistry, and there is the dreaded multiple choice section to answer. So I'll split it in half because the multiple choice can take a long time to answer. If you've been taught by me before, you'll know that my biggest piece of advice on all these papers, even going into the second year of A2, where you do the 3 papers in A2, is do the multiple choice last because it can be a nightmare and can waste a lot of time. So without further ado, then we'll go on to section A, which is going to be the only part of this video. It says you should spend only 25 minutes on this section. I would argue you should spend a bit less than that if you want to give your full attention to the rest of the paper. However, like I say, I'll run through each question and explain how to arrive at the correct answer. One thing I will say, particularly with this paper, obviously this is a past paper in its entirety, just split into 2 videos. The best way to make use of this, in my opinion, is to have a go at the paper first. So find the paper, it's freely available on the OCR website. Answer all the questions and then look at the video. Okay, watching me do it is fine because I know I'm going to get all the answers right, but you will not know where your shortcomings are unless you actually try and have a go at the questions first. So you can do it one of 2 ways, I suppose. Either, do the paper first in its entirety under time pressure, or, as I get to each question, pause it, have a go, and then resume. But in any case, we'll get on with it then. So, number 1, nice easy question to kick off with. Which compound has the highest boiling point? So this, as soon as you hear boiling point, we're looking at bonding. And basically whichever has the strongest bonding will have the highest boiling point. So ethanol, heptane, sodium chloride, and water. So let's just quickly break these down. What type of compound are they? Well, ethanol is simple covalent. Put simple cov. Heptane is also a simple covalent, simple cov. Sodium chloride, NaCl, is ionic. And water is also simple covalent. So I don't actually need to worry about intermolecular forces here, because hopefully, as you're aware, that in terms of strength of bond, ionic bonds very strong, and all simple covalent compounds will have things like London forces, permanent dipoles, or hydrogen bonds, which are significantly weaker than ionic bonds. So just by virtue of this being ionic, sodium chloride must be the correct answer. So once you've identified the correct types of bonding, it's very, very easy to spot that sodium chloride will be the highest. I think its melting point is about, boiling point, that's even more. I know it melts about 800 degrees, probably boils down slightly higher than that. So yeah, nice, straightforward. You could probably answer that in about 15 seconds if you went through them quickly. Right, number 2 then. It gives you electronegativity scale. It gives you the electronegativity, which is great because all you now have to do, you haven't got to remember them yourself, they give you the numbers. Which bond has the correct polarity? So remember, so whichever one is delta minus is going to be the higher value. So delta minus is the higher number. So you have to compare the 2. So let's take a look at the first one. In this case, it's always best to work through them in order. So nitrogen and iodine. So nitrogen is 3.04. Iodine is 2.66. And so nitrogen is bigger. So nitrogen should be delta minus, iodine delta plus. And that's actually exactly what they've done. So I'm going to hedge my bets and say the answer is A. Just to confirm to you that it is A, you can work through the others. So carbon and fluorine. Fluorine is 3.98. Carbon is 2.55. So in this case, fluorine should be delta minus, and it isn't. Boron and chlorine. Cl is 3.16. Boron is 2.04. Chlorine is bigger, so should be delta minus, and isn't. And for bromine and chlorine, Okay, and chlorine is 3.16, bromine 2.96, chlorine should be delta minus and isn't. So those three are incorrect. So again, trial and error, you know, sometimes you'll arrive at the answer immediately, other times won't, but that is a very, very nice straightforward question, particularly because they gave you the numbers. That would have been a harder question if they hadn't given you the numbers and you didn't expect to remember the trend in the table. Number 3 then, compound that releases hydroxide ions when dissolved in water. So hydroxide are released by alkalis. So you're looking for the alkali. So let's go through them in order then. CH3COOH. Now, if you draw that out, hopefully you can see very, very quickly that this is a carboxylic acid, and therefore it is not an alkali, so it is absolutely not ethanoic acid. HNO3 is nitric acid, so definitely ain't nitric acid. H2SO4 is sulfuric acid, again, and by the way, these should be common knowledge, okay, so you should be able to spot these, you know, these symbols HNO3 and H2SO4. You should know these are nitric acid and sulfuric acid. This is, you know, basic knowledge from, should be from GCSE really, but definitely basic knowledge from the A level. NH3, definitely the right answer. It's ammonia, and it is a weak alkali. So when you add it to water, you end up with NH4 plus and OH minus formed. So that is correct. It's ammonia. And again, basic GCSE knowledge. Again, you know, all, you know, in fact, it's 3 of these are acids. 1 is an alkali. Nice and straightforward. Right. Which alkane is 82.8% carbon by mass? So the easiest way to do this is to simply add up the molar masses of all of them. So it can be a little bit of a drag here, but let's just take CH4 for example. Carbon and 4 hydrogens, so the MR equals 16, and carbon is, there's 1 carbon, so 12, so 1 C, 1 carbon, all right, 1 carbon. Therefore 12 over 16 is your percentage by mass, well, times by 100 of course, is your percentage by mass of carbon, so obviously times by 100, and you get 75%, so that is wrong. It's got to do that for all of these. So again, it's working through in order. Again, there's probably a better way to do it, but in terms of ensuring you get the correct answer and you've got a method that works, you may as well just stick to a nice easy trial and error method. There's only 4 options. You can do this very, very quickly. So for ethane, molar mass is 30. You've got 2 carbons. This is the mistake people will make now. 2 carbons, therefore it's 24 over 30. Okay, and 24 over 30 is 80%. Well, times 100, of course. Third one, C4H10. So we've got a bit bigger now. So 4 times 12 is 48. Obviously, plus 10 is 58. So the MR of 58. We've got 4 carbons. Therefore, we need to do 4 times 12, 48 over 58. Times by 100, of course. 48 over 58 is 82.8. There you go. So it's 82.758 blah blah blah, which is 82.8, which for all intents and purposes. So the answer is C, and you don't need to do D. So again, the trial and error method, a worst case scenario, you have to do all 4. A best case scenario, you only have to do 1 of them, but it's just about, you know, carbon by mass, how much carbon is in there compared to the total molar mass. So total molar mass at the bottom, so number of carbons times by 12 to give the mass of carbon over the molar mass times 100, you get the percentage. Again, so far 4 multiple choice questions, all of which are very, very straightforward. Okay, very, very straightforward. So number 5, which gas sample has the greatest mass at room temperature and pressure? So unfortunately, again, it's another little trial and error approach. We're looking for the mass. We're given the volume at room temperature and pressure. So because we've got the volume, we can use our RT. So because RTP, we can use the molar gas volume of 24,000 centimeters cubed per mole. Okay, so there's 24,000 centimeters cubed in a mole, and we've got, you know, 50 of argon. So the first thing here is to work out the amount of moles of each one. Okay, that's going to be your first task. So first thing you need to do then is just take all these numbers and divide by 24,000. Now you might think at this point, what's the point? And you might be right in saying that, because if you notice, if I divide all these numbers by 24,000, it really isn't doing a fat lot. So I'll get to this part of exam technique in a minute, but I'll just do it to show you the correct method. So this is 0.002. 100 over 24,000 is going to just be 0.004. And then I'm imagining 0.006 and 0.008. Again, did we need to do that? Probably not, but I'm just showing you the correct method so you can figure it out for yourself later on. After this point, all you need to do is then take the number of moles and multiply by the molar mass to get the amount in grams. So we'll take, I have rounded these numbers, but it's not going to make a difference, I don't think. So argon times 39.9, and we get, for this one, I've just put it in the way, haven't I? So 0.0798 grams. For oxygen, 0.04 times 32. I get 0.128. For nitrogen, 0.006 times 28. I get 0.168. And for neon, I'm multiplying by 20.2, so 0.008 times 20.2. And I get 0.1616 moles. Therefore, you just have to look for whichever one is the biggest number. The biggest number is 0.168, so the answer is C. So that's the straightforward method. Okay, you work out the number of moles and then you use times by the MR. Let's put times by MR there so you know what I've done. And you get the answer. Now, did we need to divide by 24,000? The answer is no, we didn't. Because dividing by 24,000 just changes all the numbers by the same amount. Okay, if you divide everything by 24,000, you may as well divide nothing by 24,000. If you just multiplied these starting numbers by the molar mass and picked the biggest value, you'd get the correct answer, because it's the same thing. It's just shifted slightly. The numbers will be much bigger and it won't technically be moles, but it's a bit of exam technique. If you don't want to waste your time dividing all these numbers by 24,000, if you understand that by doing that, you're effectively just doing nothing. You're just scaling the numbers to a different amount. They're still separated by the same difference. Instead of being separated by 50, they're separated by 0.002. Doesn't matter. You're still going to multiply them by the molar mass and pick the biggest anyway. So you don't actually have to do this step here. If you want to, because it's the correct method, by all means. But if you're a bit more, if you understand more, in terms of conceptually how this works, you really can just skip that bit. There's no need to do it. Right. Student mixes some potassium hydroxide with calcium hydroxide. They want to know what the concentration of the OH is in the ensuing mixture. So essentially, all we're going to do here is just work out the amount of hydroxide in moles in each part and then just work out a new concentration. So first things first, then I've got 250 of 0.1 KOH. So we'll just do number of moles equals concentration times volume, and we'll do 0.250 times 0.1, which gives me 0.025 moles of KOH. And because when KOH dissociates, you produce 1 mole of K plus and 1 mole of OH minus, then 0.025 moles is the amount of OH minus. Okay, so that's the amount of OH minus produced by KOH. So for KOH, it's that. For CaOH2, the number of moles is concentration times volume. And this time it's 0.750 times 0.1, which is 0.075. That's the number of moles of calcium hydroxide. Now, when calcium hydroxide dissociates, it goes to calcium 2 plus and 2 OH minus. So you've got a 1 to 2 ratio. If I have 0.075 here, okay, I'm going to have to double that for the amount of OH. So 1 calcium hydroxide produces twice as much OH minus. So actually the amount of moles, so the amount of moles of OH minus produced in this part is 0.15 moles. So in this first one, remember 0.025, 1 to 1, 0.025. So that means in total, so total OH minus in moles is 0.025 add 0.15. So 0.025 add 0.15 gives us, I've multiplied it on my calculator, that's my bad, plus 0.15, thought looked a bit low, 0.175. To be fair, why did I even need to calculate for that? This is just my exam brain going into overdrive, because you should always check, even if you know you're right. 0.175 moles. Now we need to work out the concentration in the resulting mixture. So the resulting mixture, okay, the resulting mixture is going to be 250 centimeters cubed added to 750 centimeters cubed. So the resulting mixture, so the volume of the resulting mixture is 250 plus 750, which is 1000 centimeters cubed, which equals 1 decimeter cubed, and that makes our final sum a damn sight easier, because the new concentration is moles divided by volume, and believe it or not, 0.175 over 1 is 0.175, and therefore the answer is D. So, common mistake here, and this is where people will make the mistake, is not realizing that calcium hydroxide produces 2 moles of OH minus. If you continue and just use 0.075 and 0.025, you will get B as your answer, which is wrong. So just be aware of that. Okay, you'll get 0.150 if you forget to add the amount of potassium hydroxide, and you'll get 0.025 if you get to add the amount of calcium hydroxide. So all three other options are common mistakes. So just be aware of that going forward. Right, number 7 then. Solution is delivered from a pipette. A droplet remains in the tip of the pipette. How should they ensure the pipette delivers the volume stated on the pipette? So, this is a very important thing with pipettes, and it's something that you should always be aware of. Okay, so a pipette, this is where I'm going to draw a pipette now. This is going to be disastrous, by the way. So, actually, that's not too bad, actually. That's not too bad. That's actually pretty awful, but you get the idea. So, the pipette has, 25 centimeters, you've got a meniscus somewhere up there. When you fill the pipette, you get to the mark, meniscus on the mark, and you empty it, and let's say it's 25 centimeters cubed. When the pipette fully empties, if there was a drop left in the bottom, the most important thing to remember with pipettes is you don't do anything at all. Okay, you do not need to take the last drop out of the pipette. It is actually designed to stay there. Okay, so it's already being taken into consideration. The only acceptable answer here is B. You leave the droplet in the tip. Okay, you don't shake it out, you don't use a propeller to force it out, and you don't fill it up higher to compensate for it. Okay, A, C, and D are effectively all trying to either get the droplet out or adding more solution. Okay, the pipette is calibrated so that it leaves a small drop in the bottom, which, like capillary action, it won't leave, and the meniscus is placed. So the meniscus line, the mark is placed such that when your meniscus is on the mark, you will have exactly 25 centimeters cubed, including the droplet left over. So please don't ever get into the habit of saying you need to do something with that. You don't. You leave the droplet in pipette and move on. Right. Number 8 then. Order of increasing ionization energy. So all we've got to do is look at the elements that we're given and look at the ionization energies that we would expect. So in terms of this question, there's a few things we need to consider. Okay, so ionization energy typically increases across a period in the periodic table. However, there are some notable exceptions. remember that when I go from group 2, I put G2 to G3, group 2 to group 3, there is a decrease in ionization energy because you're going from the s orbital to the p orbital. So there's a small drop in ionization energy, and there's also a drop in ionization energy from group 6 to, no, hang on, which one is it? Group 3, 4, sorry, group 5 to 6. Okay, so group 5 to group 6, because it's very important, this as well, because when you go from group 5 to 6, there is also a drop because you are now pairing electrons in the p orbitals. Okay, so just to remind you what that looks like, when you're filling up the electrons, you fill up 1, you fill up 2, you fill up 3. When you go to group 6, you have to pair an electron, and by pairing that electron, you lower the ionization energy because of electron-electron repulsion. Okay, so the ionization energy lowers. So let's just bear these things in mind when we look through our things. So what's the first? So let's go through in order. So for A, so sodium is less than magnesium, is less than aluminium. So I don't agree with that. Okay, I agree that magnesium is bigger than sodium. Okay, so that's group 1 to group 2. However, as we've just said, group 2 to group 3, there is a drop. Magnesium is group 2, aluminium is group 3. So actually, magnesium is bigger than aluminium. So it can't be that one. For the second one, magnesium to aluminium to silicon, again, it's the same problem. We're going from group 2 magnesium to group 3 aluminium. It's the same issue, they've just put it in a different row. Should be the other way around. That's wrong. I agree, by the way, silicon is bigger than aluminium. But again, the magnesium to aluminium I have a big problem with. Right, part C, yeah, option C, aluminium, silicon, phosphorus. So that's group 3, group 4, group 5. I don't see a problem there. We don't have any decreases. We're going across the period. I think that's correct. Let's just confirm that by going to D. So D is silicon, so that's group 4, group 5, group 6. And again, as we said, as we go from 5 to 6, it should drop. Phosphorus should be bigger than sulfur. So that's wrong as well. So the answer to that question is C. All to do with just trends across period and knowing between which groups you have this small decrease. Which element has the largest number of unpaired p electrons? So this is nice and straightforward. I don't think there's a lot of difficulty here. You simply have to look at the outer shell of each atom. Okay, don't worry about the whole thing. Just look at the p. Just look at the p on the outer shell. Don't worry what row it's on. So aluminium is in group 3. So it's your 1s2, 2s2, 2p6, 3s1, 3p1. So aluminium is 3p1. So it's got one unpaired electron. Oxygen is 2p4. And because it's 2p4, it looks like that. So it's got 2 unpaired electrons. Chlorine is 3p5. So 1, 2, 3, 4, 5. It's got 1 unpaired electron. And phosphorus is 3p3 and has 3 electrons, all unpaired. Therefore, the answer is D, phosphorus. Again, you don't need to worry about Li electrons that are lower down because the shell's full. You only have to worry about the outer shell. So, number 10 then. Nice straightforward question. This screams Hess cycle to me very, very quickly. So it shows you enthalpy of formation in the table. Okay, now, because it's showing me enthalpy of formation, and I want to work out enthalpy of combustion, then my arrows actually need to go up because I'm using enthalpy of formation. There is actually a little bit of a trick to this question, by the way, but we'll talk about the trick to it now. So I'm not going to calculate it. I'm just going to tell you what the answer is just by looking at it. So first things first, okay, just a bit of exam technique. They're asking for the enthalpy change of combustion, okay, because it's combustion, okay, delta H must be negative. It's a combustion reaction. So C and D are immediately ruled out. Now, A and B, one number is big, one number is small. All we've got to do now is just look at the values in the table. and think about what we're going to do with them. So, for example, we know that because I've got 3 moles of carbon dioxide and 3 moles of water, I've got to multiply these numbers by 3. Each of these numbers has to be times by 3 at some point. That's going to be a pretty big number. That's nearly 2,000. And because of that, I know, without actually doing the question, that the answer is going to be A. Because by times those numbers by 3, the numbers are going to be too big. I'm going to have too much on this right-hand side, and if I'm only going to compensate it with 20 on the other, it's almost definitely 2060. Now, that's just exam technique. You can just look at this and do no mathematics and figure it out. However, just to prove to you that it is correct, okay, for the Hess cycle then, I'll quickly do it. C3H6 plus 4.5O2, which has no enthalpy of formation, goes to 3CO2 and 3H2O. I'm given formation data, so the arrows have to go up. The constituent elements are on the bottom, so it'll be 3C plus 3H2 plus 4.5O2. Doesn't matter about those. Right, left-hand arrow is plus 20. Right-hand arrow is 3 times minus 394 and 3 times minus 286, all combined together. So 3 times minus 394 plus 3 times minus 286 gives us a grand total of minus 2040. And in order to figure this out, I'm going to go down this arrow. So I'm going to flip this from plus 20 to minus 20. And I'm going to add minus 2040. So minus 20 plus minus 2040. And lo and behold, I get minus 2060, which is my correct answer. So there you go. Bit of exam technique there. Okay, so you don't even need to do any mathematics to work this out. Because as soon as you multiply these two numbers by 3, you know you've got far too big of a number to get an answer of 700. You will get by the way, you would get 700 if you forgot to multiply these numbers by 3. Okay, and you'd get a positive answer if you put these arrows the wrong way around, if you put them down instead of up. Moving on then to question 11. Okay, so this is a Boltzmann distribution question. Again, so 4 different graphs. It shows a gas at 2 different temperatures, and the simple question is asking which one shows the dotted curve at a higher temperature. So we need to recall what happens when we use a higher temperature for Boltzmann. So when we use a higher temperature for Boltzmann, the particles should have higher energy. Okay, so that means, that's quite straightforward, isn't it? Higher temperature means more energy. So the curve should be, further to the right. So the curve should shift to the right. And because more particles have more energy, okay, the curve should be flatter. Okay, so we're looking for a flatter curve, not a flat curve, a flatter curve, where the energy is further to the right. So we can rule out C and D immediately because the curve is further to the left, which it means lower energy, so that's not good. So it's either A or B. Now, both curves are to the right. However, one is flatter and one is not. Okay, and by flatter, you could also argue further down, lower than. So for A, this is the correct answer because the curve is lower. Okay, it's flatter than it was before. And B is not correct, okay, because the curve has gone higher. So the important thing to note is when Boltzmann distributions have higher temperatures, the curve gets lower and to the right-hand side, so it flattens out a bit because you have more particles at the end here. Oops, missed that a bit. More particles at the end are above the line and they have to come from somewhere, okay? The area under both curves should be identical. So when we look at this, let's get rid of that, looks a bit confusing. All this extra section that's above the line, the original line I should say, has to have come from somewhere.
and it comes from the bulky part of the curve at the top. So therefore it must lower as it spreads out. So nice straightforward Boltzmann question. Going on then to question 12. Nice straightforward question on dynamic equilibrium. So all you got to do is go through the statements and figure out which one is wrong. So let's take each statement on its merits. So for A catalyst increases the rate of both forwards and reverse reactions by the same amount. I have no issue with that statement. That is correct. So this is why a catalyst doesn't change the position of equilibrium, especially in dynamic equilibrium, because the rate of the reaction going forward speeds up at the same amount as the backwards one. So I'm okay with that. That's fine. B, dynamic equilibrium exists only in a closed system. Again, I agree with that. That's one of our definitions. Okay, if you ask what the features are of a dynamic equilibrium, one of those features is that it's a closed system. Now, C, the concentrations of the reactant and product are equal. I don't agree with that. And I don't agree with that because the concentrations do not have to be the same. Okay, what this is saying is if you know, in order to be in equilibrium, you must have the same amount of reactants and products, and we know that to be false because you can very easily create an equilibrium where you have, 2 moles of one, 2 moles of one substance and half a mole of another substance, and you can still get an equilibrium. So I believe this is the incorrect statement, so the answer will be C. Just to convince ourselves of this as being the truth. For D, rate of the forwards reaction equal to the rate of the reverse reaction. That again is another definition. That's a feature of our equilibrium. The speed of the reaction is the same, so it appears as though nothing is happening, even though something is happening. Okay, so the rate of the force is the same as the rate of the reverse. That's the correct sentence, so C is the answer. Right, number 13 then. The number of unsaturated isomers, structural and stereo, that have the molecular formula C4H8. Now, these questions can be complicated because, first of all, we have to unpack the word unsaturated. So if something's unsaturated, it means it contains a carbon-carbon double bond. So C4H8, let's see what we can draw then. So we've got 4 carbons in a row. Feel free to just draw these out, by the way. 4 carbons, stick a double bond in. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So that's one of them. Okay, but-1-ene. That's the first one. So now we need to look at what the other ones could be. So but-1-ene is there. I imagine we could have but-2-ene. And there's 2 different versions of but-2-ene. And I'm going to draw it like this deliberately, because that's the first version, and that would be a cis version, okay, because the priority groups are on the same side of the double bond. And you could also have the trans version, where you have priority groups on the opposite side of the double bond. So there are 3 of them. So there's 3, and now we just have to see if there are any more. So I'm satisfied that there are no more options for straight chains because we've done but-1-ene. There is no alternative. The double bond can only be put in the middle. If you put the double bond in the middle, you get one of these 2 options. So there aren't any other isomers that are straight chains. However, there's 4 carbons, so that does lead us to the possibility that we will now explore that we have a branch. So based on this setup, it doesn't matter where the double bond is, okay, because they're all going to be rotations of each other. So let's put the double bond in there. 1, 2, 3, 4, 5, and 6, and then 7, 8. This one also matches, and there's no hydrogens on the central carbon because it already has 4 bonds. So this is the only conformation that is branched. You can't have any other conformations of structural isomers. This has no stereoisomers because you've got CH3s on the same carbon. So this carbon here has got the same group attached twice. So there are no isomers there that are stereoisomers. So that's it then. There are 4 isomers in total. These are the 3 straight chains, and there is 1 branched isomer to go with as well. So your answer should be B. Moving on then, number 14. This is a question that should take you literally 5 seconds to answer. What do curly arrows always show in reaction mechanisms? So, basically if I draw an arrow, what does it represent? So this is simply the movement of a pair of electrons. It is your standard definition. Okay, it's not the movement of one electron. That's definitely not. That would be a half arrow, but we don't do that at A level. Movement of a lone pair and movement of electrons in a covalent bond, those are just specific examples of B. So an arrow, a curly arrow, is any pair of electrons, no matter its location, no matter what it is, where it's from, whether it's a lone pair, a covalent bond, anything, doesn't matter. It's just a movement. So C and D are just sub-definitions of B. So it's definitely not C or D either. Those are just describing a more specific aspect of B. So it's just any pair of electrons, that's how they're moving. It should take literally 5 seconds to answer that one. Number 15. So, structural isomer of C7H16. Which one has the weakest induced dipole-dipole interactions? So, in terms of this, these are intermolecular forces, and it's probably best if you try and draw these. So, I'll just draw them out. I'm going to draw them skeletally because there's a lot of carbons there. So, 2,3-dimethyl pentane. So 1, 2, 3, 4, 5, and it's 2, 3-dimethyl pentane. B is 3-ethyl pentane. So 1, 2, 3, 4, 5, with an ethyl group attached. That's the wrong position because I can't count. Yeah, if it helps put it at the 3 position, put that there you go. C is 2-methylhexane. 1, 2, 3, 4, 5, 6, 2-methylhexane. And D is 2,2,3-trimethylbutane. 1, 2, 3, 4. So 2, 2, 3 trimethylbutane. Now, as it stands, you need to just realize what causes London forces to be stronger or weaker. So they're all the same molecule, they're all the same compound, they're just structural isomers. So when we look for the weakest induced dipole-dipole interactions, what we are looking at, in order to work out the weakest, it's the amount of branching. Okay, because this directly relates to the point of contact. So London forces are stronger if the molecules can pack closely together. So essentially, more branching equals weaker attractions. So the question is just asking you which of these has the most branches, and that's your answer. So in terms of the most branches in the most different positions, the answer should be fairly obvious to you. The answer is D, because you've got 1 branch, 2 branch, 3 branches here compared to just 2 in A, 1 big branch in B and 1 in C. So D has the weakest forces because you have more branches on more carbons. Right, number 16. Which compound contains the smallest bond angle? So this just involves, drawing out the molecules and looking at the bond angles within them. Again, there's no real easy way to do this, but there is an easy way to do this. You've just got to draw them all out and figure it out. So bromoethane, start with A, bromoethane. It's nice and easy. Nice bromoethane. Here we go. Now, if we take any central atom, so take the carbon has 4 bonding pairs of electrons, so it's 109.5 degrees. So both carbons have 4 bonds, so the bond angle there is just 109.5 degrees total, and everything has 109.5 degrees. Now, the difference between bromoethane and ethane is I just take off this bromine and put a hydrogen there, and guess what? It's still 109.5, nothing's changed. So for both bromoethane and ethane, it's 109.5 degrees. they're the same compound, just replacing the bromine with a hydrogen and vice versa doesn't actually do anything to the bond angle. So I'm just going to go out on a limb here and say, because we've got two that are the same value, it probably isn't these, because you've got to have one lower than the others. So it's either B or D on process of elimination. Ethene, if we draw ethene, ethene has a carbon-carbon double bond, which counts as one pair of electron density, one region of electron density. So that means ethene has one, so this carbon has 1, 2, 3 bonds, and therefore it's planar, trigonal planar, 120 degrees. And the same goes for the carbon. So that's 120 degrees. And remember, we're looking for the smallest bond angle. And because 120 is bigger than 109.5, it's not ethene either. So we know the answer is B, because it can't be A or C because they're the same number. And if they were the same number, how could you have one answer? So we know it's ethanol, but let's just show why it's ethanol. Because on the face of it, you might wonder what the difference is between that and ethane. Well, in terms of ethanol, this carbon is the same as ethane, 109.5. This carbon is the same as ethane, 109.5. The difference is with the oxygen, because the oxygen has 2 bonds, one to the carbon, one to the hydrogen. So the oxygen has 2 bonding pairs, 2 BP, and oxygen also has, which we never seem to ever draw on, but it does have them, 2 lone pairs of electrons. Now, if oxygen has 2 lone pairs of electrons and 2 bonding pairs of electrons, it has 4 pairs total. If it has 4 pairs total, it must be tetrahedral and 109.5. However, remember, the lone pairs reduce the angle by 2.5 degrees each. So there's 2 lone pairs, so 109.5 minus 5 is 104.5, which is the actual bond angle. So ethanol is 104.5, and therefore is the correct answer. So that is just a very straightforward question that just asks you to consider every bond angle in a compound. In terms of A, C, and D, all of them are the same. Every bond angle is the same. Only ethanol has different bond angles, and it's realizing this OH is different. So, and more importantly, not just different, but isn't linear. Okay, so you might be forgiven for looking at the drawing originally and going, well, oxygen's got 2 pairs, 2 bonds, therefore 2 pairs, therefore 180 degrees. That's not the answer. But you have to consider the lone pairs. Oxygen has 2 lone pairs, okay, in this configuration. So you have to consider those, which means it's got 4 electron pairs in total, which makes it 109.5, and then you subtract 2.5 for each lone pair to give you the 104.5, which gives you the answer. Right. 17 then. Systematic name. These are very, very common questions. Again, in order to get through these questions, every single time, first of all, you pick out the longest carbon chain. So let's just go for the longest carbon chain. So let's start here. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So the answer is hex something. Okay, so I'm going to rule out anything that's got pent in the name. So it's not C, it's not D, because they've got pent in the name. The longest chain is 6, so it's got to be hex. Now, I've got 3-methyl hex 5-ene 4-ol or 4-methyl hex 1-ene 3-ol. Now, remember, when we do naming compounds, we keep the numbers as low as possible. So because the alkene is at this end, I'm going to call this carbon 1. So this compound has the alkene in the 1 position, an alcohol in the 3 position, and a methyl in the 4 position, which means the answer is B, 4-methyl hex 1-ene 3-ol. Okay, you would get A if you numbered the carbons. I'll just show you. If you number the carbons from the other end of the molecule, so 1, 2, 3, 4, 5, 6. If you follow the red numbering, you will end up with A as your answer. However, you always try and keep the numbers for the functional groups as low as possible. So 4, 1 and 3 is much better than 3, 5 and 4 in terms of overall value. Okay, so that's why the answer is B. Number 18 then, so dienes, it's a different homologous series that you aren't familiar with, but they've shown you the simplest diene, and all you have to do is come up with the general formula of the homologous series. So best thing to do in my opinion here is draw it out, because if you don't draw it out you might miss something. So that's what it looks like in terms of the carbon structure, and then you've got to put in your hydrogens. And if you look at it, you've got 1, 2, 3, 4 carbons, C4, and 6 hydrogens, H6. So C4H6, therefore, it can't be CN2N plus 2. That's alkanes for a start. It can't be CnH2n, because that doesn't work for C4H6. CnH2n minus 2, however, this one does work, because let's say I have 4 carbons. 4 times 2 is 8, minus 2 is 6. So therefore the answer is C. If you minus 4, you'd get C4H4, which is not correct either. So again, nice and straightforward. Just literally draw out the structure, count the carbons and hydrogens, and work out which of the general formulae this one fits into. It only works for one of them. Number 19, absorption of radiation. This is a bit of a strange question. It's not something that comes up very often, but it's always something that you need to consider, because infrared, of course, is on the spec. So there's and of course UV as part of free radical substitution means that it is absolutely a possibility that they might ask this question. So let's go through each one in turn then. So absorption of IR radiation breaks covalent bonds forming radicals. Well, that's wrong, because we know from our radical substitution that it's UV light, not IR. Absorption of IR radiation causes covalent bonds to vibrate more. I agree with that, because if you think about why infrared spectroscopy works, it's because the bonds vibrate given certain wavelengths of radiation, which gives us our our standard peaks at the wave numbers that we have. So it is a vibration from the IR. Just a reminder, just to run through the last two then. So UV radiation is eventually with global warming. No, that's infrared radiation. They've got the radiation the wrong way around. And absorption of UV is using modern breathalyzers. Again, that's not true either. It would be IR radiation again. So it must be B. Okay, so it's just about understanding what IR radiation is and how it works in terms of IR spectroscopy. Final question then on the multiple choice section. Repeat unit when addition polymer. What is the monomer? So the easiest way to do this, it sounds really silly, but just draw out what you've got. So basically just take the repeat unit, stick a double bond back in. Okay, get rid of these 2 bonds here that have come out and draw it. So C, double bond C. I'll keep going. CH2OH is what we've got. Okay, it's also got a hydrogen coming off of it. Hydrogen, hydrogen. That's the monomer. Match it up to whichever one's, basically what is this in terms of skeletal formula? Well, if you want to draw it, okay, so you've got 1 carbon, double bond, another carbon, OH. So it's A. There you go. Nice and straightforward. Okay, so if ever you want to convert a repeat unit back to the monomer, just stick the bond, okay, in between the central 2 carbons, remove the bonds that go through the brackets, and draw what you've got left behind. Convert it to skeletal if you want to, but you'll find that all the other answers simply don't work. So there you go. So that is the multiple choice section of the 2021 breadth paper. And in the second section, I'll be going through, so in the next video, I'll be going through the second section, which is the written responses.